All right, in this example, this is the asteroid Apollo, and we're looking at, it has a period, capital T, of 478 days, quote unquote Earth days, and its orbit is approximated by this equation here, where R is measured in astronomical units. Okay. So we want to find Apollo's eccentricity and the equation of its directrix to begin with. All right, so to do that, I'm going to convert the form of this. So this is number one. If I factor out a 9 from the denominator, I'm going to get 1 plus 5 over 9 cosine theta here. And so reducing the 9s to 1, this then becomes 1 over 1 plus 5/9 cosine of theta. So we know that since our eccentricity, this is our eccentricity, and its value is 5/9, which is less than 1. This is an ellipse. We can also then use the top here we have something of the form ed over 1 plus e cosine theta. This is our form here. All right, so using this relationship, we know that this can imply that 1 is equal to the eccentricity, which is 5/9, and the d is for the directrix here. So taking the reciprocal, then this implies that the directrix is equal to 9 over 5. And if you look at number 3, in the notes, it says that when you have this form, that the directrix will be to the right. And so this is going to be a vertical directrix. And so x is going to equal 9/5 is the equation of the vertex in Cartesian coordinates. So this is the end of part 1. And now we want to calculate the area swept out. So number 2, we want to look at theta being bounded between pi over 2 and negative pi over 2. So this is our region that we're concerned about, and we're looking at the area swept out by this point. We'll use this calculation from number 2, and it looks like the last problem, number 6. Okay, so we're going to have the area is equal to 1/2 integral from negative pi over 2 to pi over 2 of 1 over 1 plus 5 over 9 cosine theta squared, d theta. All right, so to integrate this, you can do a couple of different approaches. A u sub is probably the most direct. However, I'm going to use technology, and inputting this into GeoGebra, we end up getting the simple result of 14 over square root of 14 over 31/36, and then that's going to be times a bunch of stuff here. So we have 729 pi plus 29/16 arctangent of 2 square roots of 14 minus 9, all divided by 5 minus 180 times the square root of 14. Okay. So there is the area that this thing, and so this is approximately, if I do a numerical value of this is the exact value, and numerically this comes out to be about 0.904 astronomical units squared. Since it is an area, so that's the area that this thing is swept out, going from over this region. Okay, so that's part 2. Now part 3 asks to calculate the length of the major axis, knowing it's 2a. So 3. So just a sketch of the ellipse. Didn't mean to do that. So let's Well, that's a horrible ellipse, but hopefully that makes sense. So the length of the major axis, we know that this opens along this, so it kind of looks like, oh, I drew a hamburger here. So the center of the ellipse is here, and so what that's saying is that this length here is 2 times a. And so if you look, the hint is corresponding to, well, what is the angle of this value here? Well, this is along the angle that theta equals 0, and then its complete opposite direction here is when theta is equal to pi. And so the hint it's asking you to recognize is that r of 0 is going to give you the first value of the ordered pair there, and then r of pi is going to give you the value there. And so if you look at then the distance between these two, so r of 0 minus r of pi, the distance of that thing is going to be twice the a term that is defined here. As a point of clarification from the confusion in class, I believe I had these marked, the foci that you see here, this distance, I think I marked, well, it should be really from the center there. So this distance here, this is actually C, and A is the entire distance from the center to the distance of the major axis here, or to the point where it crosses the center, the line going through the center here. So the distance here is A, and the distance from here, from the center to this point here, that's the thumbtack analogy that I was using. This is the distance C. Okay. It also should be pointed out that C squared is equal to A squared minus B squared, where C is again this distance, the square root of that is that distance. A is the length from the center to here, and B will be the distance from the center to the top of the semi-major axis there. Okay. So those are the relationships then. And so if we plug in r of 0 and we subtract from it the distance r of pi, we get, and so plugging these values in to GeoGebra and taking the division by 2, we get that a is equal to 81 over 56, which is equal to a. Okay, so now that we know what a is, we can determine the other values. And I think I made a mistake in the notes too, so this is also a note about. Okay, now that we have a is equal to 81 over 56, and so the length of the major axis is twice that amount, which is 81 over is 81 over 28. Okay, so this is the length of 2a, or the length of the major axes. Okay, all right. Go ahead and get a new sheet of paper and we'll finish up this problem. Okay, while we're here, we found that a was equal to 81 over 56. Okay, b squared is equal to a squared times 1 minus e squared. Then we know what the eccentricity and we know what a is, so let's go ahead and plug those in, and we're going to take a square root. So this is going to be 81 over 56 squared, 1 minus, and then the eccentricity we found from the beginning there was, you see back here, the eccentricity was 5/9. Okay, and so if we plug that in and square it, okay, and then we're interested in the positive length of this, and that would be the length of the semi-major axis, and that gives us then the value of b, and this comes out to be something super obvious, 9 square roots of 14 over 28. That's not obvious. Okay, and so here is our b term, okay, and here is our a term, and then we're asked in part 4 to calculate the length, half length of that, and so that's what the b value is here. And number 5 says, so number 5, this is 4, number 5 is asking for then the area. The area is equal to 1/2, not 1/2, sorry, is equal to pi AB, and so we get pi is times 81 over 56 times the 9 square roots of 14 over 28, and this comes out to be 729 square roots of 14 pi divided by 1568. Okay, so that is the area. Now we're going to check this, of course, across with the expectation that if we look at the integral from 0 to 2 pi of the equation of our ellipse, 1 plus 5 over 9 cosine of theta squared d theta, we would expect that the area should be exactly the same. And if we plug this into GeoGebra, in fact, you get that this is 729 square roots of 14 pi over 1568. So it checks using both methods, using the integral and then also using the provided formula. So that's the calculation then that we're looking for the total area, and we needed that also along with the results from number 2 to answer problem 6. Okay, so in problem 6 it says that wants us to calculate the time Apollo takes. It helps if I could spell correctly, to move from negative pi over 2 to pi over 2 with respect to radians. And so Kepler's law from problem part 1 there looks like we have the time t to move along elliptical orbit divided by the time to traverse the complete orbit. Okay, well, we know the bottom one here, that was given to us at the beginning. This value is 478 days. Okay, and we're after this upper value. Okay, well, what do we know? We know that this thing is equal to, according to number 1, the area of the segment of the elliptical segment. Elliptical, it helps if you know how to spell these fancy words. And we're going to divide that then by the area of the complete ellipse. Okay, so we actually know this. This is a result of part 2, number 2, and this is the result from number 5. Okay, all right, so all we need to do is plug that information in, and then we can get our results. So we have that the time we're looking for is equal to say number 2 divided by number 5 times 478 days. This ratio turns out to give us, in decimal form, it's about 0.16. 0.165 times 478 days. Okay, so this is the ratio amount, and 478 days is the time for the complete orbit. And so if I multiply those two together, I get about 79 days. So we can just call it 79 days. Okay, so the time it takes for Apollo to go from negative pi over 2 to pi over 2 is about 79 days. All right, I hope that was helpful, and I'll see you in the next video. the notes, which I'll fix. Okay, so I need to fix that. I think I had those two reversed in the notes. So I have here that A is